Hey guys, for our project we'll be discussing the impact of hockey pucks, which is all done by Andrew Hickson, Zoe Knowlton, Victor Amparo, and Hannah Dodd. Essentially, we are conducting an analysis of a collision between two hockey pucks on an air hockey table. Our focus will be studying the forces of how they affect the motion of our two pucks. Going into the project, we decided to include some assumptions. For the first assumption, we decided that friction is negligible since we are using an air hockey table. The second assumption is that we viewed our pucks as particles. We calculated the puck's movements from their center of gravities. For the third assumption, we decided to make the small puck and big puck have identical masses since the pucks were 3D printed. For the fourth assumption, we decided that the table is perfectly flat and uniform. The last assumption is that the initial velocities of each puck is exactly what we say. We claim that our velocity recording method was to be perfectly accurate for the sake of the study. In terms of the constraints, we only had one in which we had to make it in 2D motion. The hockey pucks were moved on a table and made it easier to map their motion on an XY plane. For our simple calculations, this demonstrated how we calculated our data. The equations that we used were the conservation of momentum and the coefficient of restitution, which is the relative velocity after the collision divided by the relative velocity before the collision. The coefficient of restitution can range between 0 and 1. When the coefficient of the restitution is 0, it is perfectly inelastic where the objects can stick together after the impact and kinetic energy is not conserved. Whereas on the other side, if the coefficient of restitution is 1, then it is perfectly elastic where the objects separate after impact and didn't lose any of their kinetic energy. For our theoretical data, we decided to input some of our own values. For both pucks A and B, the masses were 1 kilogram each. For puck A, the initial velocity was 3 meters per second and the final velocity was negative 1.62 meters per second. For puck B, the initial velocity was negative 4 meters per second and the final velocity was 0.62 meters per second. We chose our x direction to be positive if it is going right, whereas if it were going left, it would be negative. After plugging and chugging the values into both of the equations, we got our total momentum to be negative 1 kilogram meter per second and our coefficient of restitution to be 0.32. As you can see in our sketch, the type of impact problem we have is central impact. The dashed line going horizontally across both hockey pucks is called the line of impact, where the forces are exchanged during impact. In the line of impact, we have the normal direction in the center of mass. The solid line that is vertical is called the plane of impact, where there are no exchange of forces. Based on the sample calculation, we follow the same procedure but with our gathered data points. As you can see here from the data, the smaller pucks have a smaller coefficient of restitution, whereas the bigger pucks have a larger coefficient of restitution, and for the mixed pucks, it fell right in between both values. So to conclude, the larger pucks are more elastic than the smaller pucks.